Thermodynamics is the study of why hot things are hot and why cold things are cold. Normally I wouldn't really care about this, but it's on the AP Physics 2 test and I do care about that. Luckily, the creators of this borderline scam have blessed us with a reference paper with equations on it that we get to use whenever we like. But where do these equations come from, and how do you actually use them, and what if you instead have to look at a graph or diagram or something? Let's begin. Firstly, temperature. All things have temperature, but unfortunately, real materials have pesky intermolecular forces and stuff, so 90% of our calculations will be done with ideal gases. How this hypothetical kind of matter works is called kinetic theory, which holds that all the macroscopic properties of the fluid, like pressure, are the result of millions and millions of tiny particles flying around randomly and hitting stuff. Now, this gas sample is not moving, and there are no springs or changes in gravitational potential or balance in electric charge, so this system has no mechanical energy. But these little guys inside the gas are definitely moving, and we call their kinetic energy internal energy. Symbol U, not to be confused with mechanical potential energy, which is also U, even though neither phrase has a U in it. Anyways, now is a good time to talk about the structure of this chart. In the central rectangle, we have all the variables and constants in this unit, as well as their units, and whether they are vectors or scalars. More information about this section, as well as the ellipse just outside, can be found in this wall of text. The rest of the chart is split into 4 sections by concept, each having information about specific scenarios that often show up in exercises. Essentially, the further out you go, the less general the content becomes. The next quadrant of the chart deals with processes, especially of ideal gases, and it's where the first law of thermodynamics comes into play. We can visualize the important types of processes on a PV diagram. Internal energy, as we know, is a multiple of the product of pressure and volume, and the work done is, well, the product of force and the displacement of the gas, which is equal to the pressure times cross-sectional area times the displacement, which is all equal to parallel pressure times the change in volume. Add this up for an infinite sum of intervals, and we have ourselves the area under this curve. The negative sign does matter here. If you're not sure whether the work done on or by the gas is positive, it's helpful to draw out the directions of pressure and displacement, because you will mess this up otherwise. Most processes won't be this complicated. For example, an isobaric process has constant pressure, an isovolumetric process has no change in volume and so no work done, and an isothermal process looks hyperbolic because the temperature, which is proportional to pressure times volume, holds constant, so the two are inversely related. Lastly are the adiabatic processes. These have no heat transfer, but this does not mean that the temperature holds. Quite the opposite actually, it's always steeper than a corresponding isothermal process. Now, we just talked about what happens if there's no heat transfer, but what about if there is? That's where the next quadrant comes into play. Now, every material has a property called specific heat, which is just how much the change in internal energy affects the temperature. Yeah, the equation sheet says Q equals mc delta T, but as we saw earlier, temperature can also be influenced by mechanical work, so that's not quite it. There are 3 kinds of heat transfer that matter to us. The simplest is radiation, because literally everything radiates. It's why really, really hot stuff glows and why thermal cameras work, and this topic is so cool and interesting that College Board moved the radiation rate equation to the modern physics unit. Whatever, sure. Next up is convection. This is what happens in Earth's mantle and in clouds and in all sorts of fluids actually. Lastly, and probably most importantly, is conduction. This happens because at a microscopic level, the particles in 2 touching objects will hit and exchange some energy, and those particles collide with other particles further in each object, and so on and so on and so on until internal energy has been sent through the entire system. Because the particles and gases are spread so far apart compared to liquids and solids, they are terrible conductors. This is why you can stick your hand in a microwave just fine, but as soon as you touch that stupid plate, it burns like hell. Although the air and surface temperatures in the microwave are quite similar, the cells in your skin detect the gradient of heat transfer, not the temperature difference. Anyway, let's talk about something scarier than burning your fingers like an idiot: the demise of the universe itself. You've probably heard entropy described as amount of disorder. This is okay, but it doesn't connect easily to other concepts in thermodynamics, so I'd like to propose a new definition in between it and the actual definition, which neither of us really need to worry about, I hope. Entropy is a measure of the likely variance in a system. Okay, take the set of 3 dice. In system A, all 3 are in a single stack near the center of my desk, while in system B, they're scattered all over the place. System B has more entropy, because although we don't really have much information about either system, system B's can mean a ton of very different configurations, while system A has relatively few. And this is how we analyze systems of actual matter. In a gas, for instance, there are so many particles moving it so unpredictably on their own that we use probabilistic models to describe describe their composition. This is known as statistical mechanics. At higher temperatures, a sample has much greater spread in particle speeds than at lower temperatures, so the former has greater entropy. Likewise, mechanical energy such as kinetic energy is, practically, distributed consistently through a sample, whereas internal energy is incredibly variable, so a system with mostly internal energy has greater entropy. The second law of thermodynamics states that the entropy of a closed system cannot decrease over time. Take this piece of paper. If I rip it in half, I can't just put it back together. I could melt it down and run it through the paper-making process again, but that would waste a lot of energy as heat, so overall entropy would still increase. You can convert internal energy into mechanical energy through processes called heat engines, but these cannot be 100% efficient. Each cycle still loses energy unless you're at absolute zero at some point, which isn't possible. The second law also bans perpetual motion machines from existing. You'd have to have no friction, no radiation, no non-conservative intermolecular forces, which is impossible, so any kind of complex systemic movement will eventually disintegrate into chaos. On a human scale, this really isn't noticeable, but after billions and billions and billions of billions of years, everything will fall victim to this rule. The universe will just be a sea of subatomic particles whizzing around at relativistic speeds for eternity. This is known as heat death because all mechanical energy has been lost to the sundry kinds of heat transfer, and as far as we know, there's no way to stop this from happening, so until then, enjoy your time left on this slowly dying planet. Also, the shape of the heat engine processes on a PV diagram doesn't have to be rectangular. It can be any closed clockwise loop. The heat pump can similarly be any closed counterclockwise loop. Okay, now we're done. Now we're done.